Today's topic is application performance in the cloud. And before we jump into the aspect of performance, I'd like to spend a little bit of time on the definition of what a cloud is. And I know, from my experience, cloud is a very hot topic, and people, talk about cloud and virtualization. And a lot of times they equate cloud with certain technologies where, in a sense, in my view, it's not really about specific technologies, because cloud could be considered kind of an off-premise where you deploy applications outside of the enterprise, or on-premise. Also, it's really about the properties of the underlying infrastructure, underlying application that you're talking about. So, for example, one of the main qualities of a cloud is elasticity, right? So just moving an application, let's say, off-site without having to have any elasticity, while the application may be running off-premises, it's not necessarily, in my view, would be considered to be a cloud application. So if you look at the qualities of cloud, you typically find elasticity, agility, typically the use of, or the ease of deployment, that you deploy application once and it's available to everybody, independence from hardware, software, or at least to the users, complete transparency, and typically it's also associated with the fact that it's pay per use, so you get to use it as you get to pay for it as you use it, sometimes for free. But in many cases, what you find is applications in the cloud doesn't have to be obviously on-premise or off-premise. In fact, you can have cloud environments deployed within the enterprise itself, right, which we call private clouds. And you can have also hybrid cloud deployments where you have applications maybe deployed internally, and then you may offload to a public cloud if you need more capacity. So there's a variety of different models that could be used when we talk about cloud applications. Now here, because clouds in generally have a variety of different qualities, here we're really going to focus on performance. And what does it mean for applications to be deployed in the cloud, whether on-premise or off-premise, and how do we define performance? And as you could actually see, as you break it down, the stacks in the cloud, you have infrastructure as a service, you may have platform as a service, and application as a service, or what some would refer to as software as a service. So you would find that, for example, in infrastructure as a service, it's kind of, it's fairly straightforward to define what performance is. For example, if I were to get an infrastructure, for example, from Amazon, I know I'm buying CPU, I'm buying memory, I'm buying storage, and I'm buying, network bandwidth. So it's fairly easy to measure those. As I'm moving up the stack into the platform, it becomes more and more difficult to quantify and define what performance actually means. And as you go up to the application, it becomes very much application-centric. What does it mean for an application to perform in the cloud? So what I'd like to do is kind of focus on that question. And the other part is obviously how do we ensure application performance in the cloud. So if we kind of, simplify cloud deployments a bit, and I know cloud deployments, obviously on-premise and off-premise could be quite complex, but if we just break it down into tiers and stacks, I think what you would find is you have, again, an infrastructure as a service, again, could be EC2, could be Azure, could be your own homegrown infrastructure as a service, for example, built on VMware and some other virtualization technologies. You've got platform as a service, which typically consists of, application servers, middleware, a fabric basically that interconnects applications. And then you've got applications, right? Again, this could be web-based applications, this could be business applications. It's really application specific. And if you start breaking it down, obviously the user is at the top, you find that applications, as the problems occur in different tiers, they tend to escalate. An example, if we have an issue, for example, an infrastructure such as a CPU may be completely pegged out, on a set of servers, that could quickly escalate. And obviously, the users may perceive a slowdown, whether it's a timeout or whether they're not able to perform what they're supposed to do. Now, essentially, what you will probably see is that this problem will amplify itself. So the platform will start misbehaving in many different ways. You may have different kinds of symptoms. And in the application, you may have an amplifying effect in the application and again, the user. The other thing is, would be to consider is what we call, keep switching, the level of impact and visibility, right? If the problem occurs in the infrastructure, you can kind of isolate it in the infrastructure, you can fairly well contain it. But as the problem travels higher, that visibility becomes very pronounced, especially for web or customer-facing apps, right? Customers that discover these problems will typically become very annoyed. They call. Obviously, with the social networking, they can, these problems can propagate very quickly. So if you're like an e-commerce type application or you're a front-facing app, it's very difficult to contain these kind of problems. So one of the things you want to do is be able to monitor applications, and then we broke it down into a variety of different key performance indicators if you actually break it down by tiers. For the application, it's very important to look at the user experience. And a couple of things that obviously is very important also is, are you able to handle, for example, multi-tenancy and other aspects of that. And as you travel down the stack, you'll find the different levels of performance that you actually need to look at. For example, in platform, it's about clustering, it's about interconnectivity, it's about data sharing, workload management. In the infrastructure, it's about virtualization, resource allocations, and making sure that you have enough horsepower in order to support your app. But in the application itself, it's, as we'll see further in the slides, it's actually very difficult to quantify what the performance is. And most people will say, well, maybe it's response time. But imagine you go into a website and, for example, you click and your response time is quick, but you're getting an error. That doesn't necessarily mean your application is performing well. So the application performance is a lot more difficult to quantify. And let's look at I guess the first, I would say, is the first take on application performance. And that's what typically people do when they roll applications out. So what they typically do is they look at each individual stack. So, for example, for infrastructure as a service, you're going to monitor some basic resource parameters, right? Such as CPU memory utilization. Are you running within the certain normal bands? In the platform as a service, for example, if you're Java, or it could be, Zio, CICS, or whatever it could be, I mean, they're fairly well-defined set of characteristics, although each one has its own set of performance attributes. For example, in Java, it's very important to look at garbage collection, heap utilization, for example, servlet and web response times and things like that. In the application, as you start going up, it now escalates to what does the application really care about. Now, if we're talking about, let's say, a payment app, in this case, maybe you're looking at the number of payments and how many payments and what the value of the payments that were processed. If you're an e-commerce site, it may be a completely different set of performance attributes. So again, that's why it's kind of difficult to determine, and I think it's challenging for a lot of enterprises to measure application as a service because they're not really standardized. So the first take is really what people are doing is really looking at each of those tiers. Now, as we go a little bit further and actually introduce an end user, and we find that if we put that type of model in place, what you'll find a lot of times is you're going to see green lights across all the tiers, right? So your infrastructure is performing normal. Your platform as a service, in fact, could be performing normally. Your applications, even in terms of orders and in terms of the web response time and all of those indicators that we just mentioned are, in fact, normal. But what we will see is a user in fact, may be experiencing a timeout. Now, first of all, if you're monitoring just the tiers themselves or the stacks themselves, you probably won't even know that there's a timeout or the user might be experiencing a timeout. And there's a variety of different reasons why. An example would be if you're not looking at last mile connectivity, that the user maybe because of his geographic location has a problem to actually interact with the application, while it may be true that it's not your, nothing you can do about this, but from the user perspective, it may be a problem because they perceive it as, they're not able to access your service. Now, in US specifically, as I found, last mile connectivity may not be a big problem, but I traveled actually outside the United States. In fact, just recently was in India, and for them, last mile connectivity was a big issue. For example, a person who's, going on trading and trying to buy a stock, and they're in some environment where they can't access a website, in fact, for them, they're trying to click on, say, I want to buy or sell, they're not able to do it. It's not really because your service is not available. It's really because the intermediate provider is having a problem. So last mile connectivity in the overall application scheme needs to be taken into account. And as you can see here, in this case, what you'll find is people who are monitoring the application will actually see all the green lights, and in a sense still have an outage. So if we look at what happens between the stacks, it becomes really important to not only look at what's going on within each individual layer, but also understand what is the relationship of how these layers actually communicate. And this actual problem becomes really kind of difficult because the topology is not very well defined, right? You have infrastructure as a service that could be fairly dynamic. You have, virtual machines that could be popping up and down. You have platform as a service that could reconfigure itself on the fly with clustering where you can have things moving around. And you have application itself that provides multi-tenancy, another quality of service that adds complexity to this environment. So you can't really build a static model and figure out what performance is without having to start looking into what's going on between the stacks. So the take two typically is once you achieve that, kind of the first case where you're looking at each individual tier, is now you start looking at, well, what is the relationship between each tier? And the take three here is really monitoring each stack, but also monitoring transactions that are flowing between each stack. Now, in this case, what do I mean by a transaction? In this case, a transaction is really a user interaction. So let's say if I go on a website or I go interact with an application and I say I want to buy something, or I want to search for something. In this case, everything that is triggered as a result of that interaction would be considered a transaction in my view, right? It's not just access to a database. It's not just, sending a message through middleware or doing something in the application server. It's really all of the individual steps that are required in order to satisfy that user's request. Now, that doesn't have to be necessarily a user as a person. It could be a background batch process. It could be an application talking to another application that's initiating a request. So it doesn't necessarily have to be a user. So if we are actually monitoring these interactions, what you would see is the user, as it enters a request, we're monitoring interactions, and we could see that the path to, in this case, a database is the one that's slow. So even though all of the indicators are showing green, we will still be able to catch that this one user specifically is experiencing a timeout. In fact, we have here, a user, Bob, that's executing a transaction. And because we're tracing interactions and we're figuring out the topology of these interactions, we're able to actually say that even though all of the things are green, user Bob is experiencing an outage, and because we may have a deadlock or a slow query that's hitting a database. So it's not enough just to look at the individual stacks and understand what's going on. You really need to look at things between the stacks. And the take three, once you achieve these first three tiers, one of the things obviously you want to get to the next one, which is well, how do I, without really looking at individual performance indicators, how can I holistically tell what my application is doing? And in this case, we're really talking about being able to proactively monitor applications and applying some trend analysis to be able to understand what's going on with the apps. So in this case, the indicators could be not just, garbage collection, not just, response times, but also looking at how the transactions are actually flowing between the different components. So in a sense here, we're looking at, for example, the users hitting a page, we're building up kind of a trend of the performance, and maybe, database is slowing down. In that case, if we're looking at the trend that's consistently going in the wrong direction, we may potentially, throw a preventive alert instead of waiting until a user actually experiences a timeout. So the next thing is really to escalate it to a point where you can proactively look at behavior of the different indicators, and then from there be able to say whether it's normal, abnormal, or whether it's trending toward a problematic state. In that case, there's no reason to wait for a timeout to occur. So that I would say is the application, I would say a take 4. To kind of contrast and compare, and again, what I see is how people are typically monitoring their environments versus what I typically recommend from these kind of 4 phases of performances. You would find that typically what people are doing is really monitoring individual components. They're focusing on specific indicators. And then it's typically focused on kind of this fault management, availability management, right? You typically get an event saying something's wrong, and then it becomes a kind of this reactive type, reactive loop back or feedback back to the application support or whoever supports the application. And in that case, remediation cycle is typically very long, right? I mean, an event could be very vague, saying CPU is high, or garbage collection is a problem, or you have a timeout, or maybe you have a response to degradation. But then the question is why? It becomes very difficult to figure that out. With transaction profiling, it really unlocks this a little bit, especially very useful in cloud deployments because of the fact that things are moving around, and you could have, in virtual environments, things are a lot more dynamic. You can't have static models. So in this case, you need to be able to automatically trace the behavior of the application and how it interacts with different tiers, whether it's an infrastructure or whether it's a platform as a service, and be able to spot where the problems are and then get down to the root cause. In this case, the remediation cycle is typically faster, as we have, for example, in the slide above, where you might have detected that there is a timeout, but it would be very difficult to answer why. In the case of tracing transactions, we would be able to actually pinpoint directly to the root cause, because as the transactions are monitored, interactions between the tiers are monitored, and therefore the association between the failure or a deadlock on a database or a slow query would be made with the original request that was submitted by the user. So that's an important distinction. A traditional monitoring, where you're just looking at kind of the KPIs and you're looking at performance, versus understanding how transactions are flowing through the environment. And then I would say the other is configuration, which is somewhat kind of complicates the story a bit, is when you have hybrid deployment. Well, here, problem becomes actually amplified, because now not only you have to monitor your on-premise assets, but you also have to then take into account the off-premise assets, right? And they're completely independent. They could be built on a different set of stacks. And then most of the, what I find is you don't really have much control of what's deployed out in the cloud, right? Whether it's EC2 or something else. Last mile connectivity now applies not only in relation to your assets that are on premises, but also the infrastructure and applications that are off premise. So depending how you structure your environments, now you have to look at both of these environments and consolidate them together. And in this case, what's actually coming up is, number one, monitoring could also be used as a service. So actually, monitoring and performance monitoring, while you could, for example, install something that's running on premises that looks at both of these environments. You can also possibly look at monitoring as a service itself. In some enterprises that may be allowed, and some for security and privacy reasons it may not be something that enterprise will consider. Now, what you also find is that you would need probably instrumentation deployed at in each of these environments, right? So if you have, for example, Java running on, for example, on-premises and off-premises, now you have to deploy instrumentation, whether it's agent instrumentation, on-premise and off-premise. In this case, you're going to have to consider things like firewalls, security, and privacy as well, because you have potentially traffic moving between the different cloud deployments. An example would be if you're tracking transactions, you would have to now consider where do you deploy your monitoring environment. Do you deploy it on-premise? In this case, the information that we're collecting, for example, in the outside of the enterprise is going to have to be somehow delivered to your management server. Think of it as a monitoring server that runs on the on-premise. So cloud deployments, while they simplify a lot of the, I would say, a lot of the development and deployment things where you can just resize and, infrastructure becomes fairly, elastic, it introduces a whole set of issues in terms of how you manage and monitor applications. One of the use cases I want to introduce here is, and actually deep dive into, is the trend analysis. And here what I want to do is actually break down an application. In this case, we start almost like with a take 4, where we're monitoring an application, we're monitoring transactions, and in this case, what are some of the tools and what are some of the methods you can use in order to proactively measure application performance. So typically, what you'd find is, in order to monitor the application, and I see people, sometimes they just focus just on the application itself, meaning only KPIs that are produced by the application. In this case, I'm really looking at a holistic approach, meaning look at the application, look at the platform, and look at the infrastructure that this application actually depends on. And typically, what you'd want to do is you want to collect enough of the samples from the different layers in order to build a relevant baseline. And depending, obviously, how far you want to trend this information, you can obviously trend it, you collect it for weeks, you can look at it for days. In this case, we're looking at more for short-term analysis, meaning you're looking at the application performance and you want to understand, where it is compared to the normal or abnormal. And then you want to be able to apply some analytics to determine whether these samples that you're collecting and aggregated are actually within the bands that you're looking for. An example for an application, what you typically want to do is look at the business KPIs, and that depends obviously on the application, but let's say it's an order fulfillment app. So you want to look at the orders, you want to look at response times, and you also want to look at, for example, in the Java world, GC, very important in the application performance. You want to look at the clustering, how that behaves, and you want to look at response time, I/O, and memory utilizations. Now, the three things we typically use, and I like to use kind of a simple approach. Obviously, there are complex models that you can apply, but if you want to really quickly understand, where your applications are compared to the normal, we typically use 3 indicators. One is what I call a Bollinger Band, or Bollinger Band, velocity, and a percent changed. If you apply these 3 indicators to a variety of different KPIs, and obviously these have to be integers or longs, it has to be numerical type KPIs, you could pretty much determine where the metric is in fact going. And it typically, what's good about it is you don't have to know anything about the application itself. You don't have to understand the topology. You don't have to understand the dependencies. Now, one of the useful ones is that we use a lot is, for example, the Bollinger Band. Basically, here you look at the set of standard deviation, you compute the mean, and then you also look at there's 2 standard deviations above, 2 or 3 standard deviations above, and 2 or 3 standard deviations below. Now, in order to do that, obviously, you have to build a historical base of several samples, typically 50 to 100 samples of the underlying metric. And that's considering that you're collecting, every 30 or 60 seconds, right? The sampling rates are 30 or 60 seconds, maybe below, depending on the kind of application. Velocity is typically about how quickly you have change in the underlying metric. So let's say you go from, 60% utilization to 80% utilization over a period of 10 seconds. Well, you take that difference, divide by the number of, seconds, and you get your velocity over, average velocity over a period of time. So, and the percent change obviously expresses the same thing in the percent move. Those are typically are good indicators to determine what's going on and whether you need to pay attention. An example would be, let's say you're monitoring several indicators and you computed the high band. In this case, anything that goes above the high band, you would want to alert on, right? So in this case, you don't want to set up a dynamic threshold where a static threshold where you say, well, is my memory, greater than 90%? That would be, probably not appropriate because in some applications, 90% may be completely normal, right? So what you want to do is build your baseline, and then from there say, well, I look at my normal band on the upper side, on the lower side, and then see where I fall. Again, percent change could be used, again, for capacity management, especially if you do it day over day, week over week, or month over month. So percent changes allow you to determine more longer-term moves in the underlying metrics to determine what you need to do from the capacity management standpoint. And velocity could be also used to determine short-term moves, especially if you have something that's highly kind of in the band, it's moving up and down, and you want to be able to determine if something is that you actually need to pay attention to. Typically, the velocity will change, and you need to pay attention to this type of move. Now, one of the things I want to caution you a little bit here is that the normal or what's abnormal could become the new normal. So, and in fact, you need a model that will actually adjust to that, right? So a move, for example, in response time to 30 seconds and staying there for a very long time, in fact, could be considered, from the mathematical standpoint, you could consider it to be the new normal. Now, whether it's acceptable to the business, that's a completely different question. And then typically you want to bundle it or layer some business rules on top of that, because no matter what model you determine, there are certain situations where you absolutely need like a human interaction. As an example, for example, we do a lot of business, for example, with financials. So for them, they need to be able to cut off, for example, at 4 o'clock, market closes. So it doesn't matter what you learn if a certain set of indicators are not in line by 4 o'clock or 10 minutes before. That could be an alert. So certain things you really can't learn through any analytics or any set of baselines. It needs some kind of rules from the actual users. Typically, what kind of instrumentation would you need to put in place? Well, on the data collectors, one of the things that people are doing is typically collect a lot of data, but it's very difficult to actually make sense of it. One of the major reasons is because all this data is really not time synchronized, right? So for example, you're collecting CPU, you're collecting response time, but you need to correlate them in time. So typically what you want to do is think of it as almost like a thread. In specific, for example, at 2 o'clock p.m., what are the most important indicators? What is the CPU? What is the response time? What is the I/O? What is the bandwidth? What is the network doing? How many orders are filled? In that case, when you collect information that way, you can actually analyze and understand how application behaves during this time sample or time slice. Otherwise, you're going to be comparing apples and oranges, right? So you may have, for example, CPU during 2 o'clock, but you don't have the network, or you don't have, for example, numbers orders filled. So you need to be able to say within a certain time, give or take, plus or minus a couple of seconds, depending on what your tolerance level is. What are all the relevant indicators that you care about? Then you need to build a history of these indicators, and obviously it all depends on how far you want to go back. Some people want to maintain history of every metric for for years, right? It depends again on your specific needs. But typically you want to aggregate that data, which opens a totally different set of issues. Where do you store the data? And how do you mine that data? It's not really something that I can address in this topic, but typically what that means is customers then want to go to other big data platforms where they can actually store all this data. So it opens a completely different challenge if you say, I want to build a history for a very long time. It opens a completely set of new challenges there. Then you need to be pattern match and analyze the data itself, obviously data mining, and then the question is how do you do it in real time? In that case, typically you want to buffer that as much of the data as possible in memory. And again, if you constantly go into the database and trying to pull that up, it will be probably most likely very slow. You won't be able to do, short-term analysis. You could do maybe long-term analysis, but not really short-term analysis. And you want to be able to do some actionable, outcomes, right? What do you want to do if we detect an abnormal condition? Take an action, send an alert, trigger a script, whatever needs to be done. Do you want to put a visualization or a dashboard? So as a holistic approach, the data collection is very important. It's, think of it as garbage in, garbage out. If you have bad data, if it's not properly synchronized, if it doesn't have proper correlations, you won't really be able to really come up with any actionable or any meaningful data. So it starts really with accurate data, analysis of history and storing of that data in a repository, pattern matching and analytics, and then obviously the actionable outcome. Another example I want to talk about is looking at a Java application. And again, this could be obviously in the cloud. It could be, on-premises or off-premises. In this case, we're looking at also an application, and we're looking at really one indicator only. For example, garbage collection. And in fact, you could tell a lot about application performance by simply analyzing some of the byproduct of what the application activity. And a lot of it, for example, in the Java world, is how the garbage collection behaves. In this case, we're looking, for example, at a garbage collection, in this case, a number of samples. We're looking at GC duration. How long does it take to actually garbage collect? We're looking at how much CPU is taken in the garbage collection, and average CPU since the startup of the JVM, and JVM heap utilization. So as we look at these, what we will find is, the first thing is that we apply kind of the multiple principles here all at once. We're building up a baseline of the indicators, and we're also setting up what we call a normal band and the upper band. In this case, as you could see, the red line is actually showing what I call an upper high band for a specific metric. In this case, we're showing, for example, GC duration. If you look at this one, we have a normal application activity down below, and suddenly a dramatic jump in the application, in the GC behavior. Now, that may potentially mean that maybe you have a whole set of new orders coming in, and the applications just suddenly went into high gear and creating a lot of objects, creating a lot of allocations, deallocations. Now, in this case, you may want to actually set up an alert, or an alert will actually be generated automatically as we breach that high band. So in a sense, there's no reason to actually set up any of those static thresholds because the dynamic high band will already have established a normal band, and then anything outside that would be a problem. So that's what we call a spike in activity, a sudden spike in activity, right? You want to be able to capture that. A typical static approach would not work in this case, right? What would be if I were to sit down and say, well, what should I have this application, it may be allocating resources, it may be going, on premises, off premises, or maybe requesting things outside. How would I determine what even the threshold would be? It would be very difficult, right? So in this case, applying that type of model would actually work better. As you could see here, I don't know, it's probably very difficult here to see the percent dispersion. What we call percent dispersion is basically how many standard deviations are you from the actual mean. So 200% dispersion in this case, or anything over 200%, is a problem. What it means is basically 2 standard deviations over the mean. If you have a negative minus 200, obviously means negative 2 deviations below the mean, right? So a sudden spike and obviously an actionable outcome right at this tipping point. But as you could see, in one of my previous slides, we're talking about a caution. A normal suddenly becomes, or abnormal becomes normal. As you could see, the band starts to adjust. And it's kind of difficult to see, but you could see it right here. A band starts to creep up, and they essentially will meet at some point, which happens right here on this graph. So in a sense, even though you've gotten an alert at this point, any future jumps into that area will not trigger any new, think of them as notifications or alerts, right? Because the high band has adjusted for this new level of activity. And as we could see here, we're no longer showing red because the level of dispersion or level of abnormality in that case is not really there anymore, right? So that jump in the new activity and then prolonged action in that new band now canceled all of these kind of anomaly in the behavior of the application. So in effect here, what we're showing is what the abnormal is now became the new normal. Okay. And one of the things I want to stress here is there's no need to really understand any of the topologies by using these approaches. Any of the topologies of their underlying, VMs, underlying, platform, underlying application. It's simply looking at KPIs, their behavior, and then figuring out normal or abnormal. The other part that I want to talk about is, and here we talk about more or less performance of, let's say, garbage collection or response times, is another area of applications which are especially important is what we call leaks. Resource leaks are a really tough problem because they're really tough to spot. Well, you could spot them when it's already late, and really, there's really not much you can do about it. An example of a resource leak would be, let's say your application server leaking memory or handles or something, or classes or class loader leaks you may have. Once you detect it, your probably JVM is already maybe at 90% utilization, and there's really not too many options you have other than probably restarting the application. Now, in cloud environments, what actually is helpful, because you can also always spin off another instance and pretty much mask or somehow hide that problem. But still, the question becomes is, if you have a set of users connected to that instance, and you have a set of resources that are constantly being consumed, it's important to be able to detect those leaks, but it's also important to analyze, what to do about them. And typically, what are the causes of those leaks? And again, a lot of the concepts that I'm talking about, they apply, to, cloud applications, but also, non-cloud applications. But as you'd find, as you deploy in the cloud, it becomes more and more important to make sure that the quality is good, right? And in this case, if you have developers, for example, working across different continents, putting the software together and then deploying it, it's very likely that you may have a resource leak of some sort. And what are the typical reasons? You're going to have, obviously, unchecked arrays. You're going to have problems in the, people are, especially in Java, because it's all garbage collected, people really don't pay attention. A lot of the developers are not really trained to make sure that they're very cautious with memory. So you end up a lot of times with bad JDBC collections, bad, interactions with the databases, not closing socket handles because they believe by just, leaving the instance, or setting it to null will close out all the resources. Well, it's not exactly true, because the applications are actually, the handles and all these other resources maintained by the database are actually still maintained. And you have class loader leaks and resources that are allocated by the JVM. So there's a variety of different problems that could occur that are very difficult to track. And what you'll typically find, this is a chart, it's kind of accelerated chart here. In many cases, you won't see that. If you see that, you'll probably spot very quickly. But in this case, any resource, obviously any finite resource that you have that has this type of chart, will typically indicate that you'll have a problem, right? Whether it's operating systems, memory, or disk space, or even in the in the VM, in a virtual space, there's still limitations on the how far you can grow and how far you can expand, and that will impact the elasticity of your cloud deployment as well, obviously. So this is a case of a pattern that will indicate a resource problem. This typically will indicate a pattern of a constant allocations, deallocations, and eventually it basically is a zero-sum game, right? You're staying at a constant level. So then the question is, well, how do you detect it, right? So I may have a cloud deployment of virtual machines coming up and down. They may be spread out across on-premise and off-premise deployments. I may have tens, hundreds of those instances running. How do I determine if any one of those actually exhibits this type of behavior? How can I catch it quickly? But also then, what can I do about it? Well, one of the things, for example, we do is we use a special, what we call Oscillator. So that's one of the analytical tools that we use. It's actually used in, I don't know how many of you do stocks. It's actually used very often in stock analysis and when people decide to buy or sell securities. In this case, we're using a very similar principle of an oscillator to determine the rise and drop in the underlying performance indicator. In this case, specifically memory. As you could see, an example, we have a multiple JVMs here at 86, 68, and 93% utilization, but their oscillators are fairly constant around 50. An oscillator typically moves from 0 to 100. 0 means it basically looks at the gains and losses over a period of time. So in a sense, at 50, which means the number of losses and number of gains over a period of time is basically 1. The ratio is 1. So 50 is where you typically want to be, or around 50. Anything above 50 or 60 will indicate a growth. Anything below would indicate a loss. And what we see here, we have one of the instances, which is a WebSphere application server instance 4. So you can have a cloud deployment, an application running, let's say, in Amazon, consisting of, let's say, 4 application servers. And this application server, while it's still running at 41% memory utilization, its oscillator is way above normal. As you can see, the pattern of that heap utilization is not a normal pattern. So you can't just go, in this case, a typical monitoring solution would be, well, I'm going to set a threshold to 90%. Well, that's a long way out before you actually determine that there is a problem. And in fact, for this JVM, it is completely normal. So it becomes very tough to figure out for the instances, especially when you have things moving around and automatically provisioned, what is normal and what is abnormal. So using the momentum oscillator, in this case, it spotted that this behavior is what I would call a leaking behavior, and somebody needs to look at it. Now, it doesn't, obviously there are cases of false positives. An example, you've got suddenly 1,000 users connecting to this new instance and causes a dramatic spike in activity. If that happens, it could be, for example, a false positive. But in many cases, it will actually determine where you need to look at. It may not necessarily be a problem, but it will flag you where you need to look. So a momentum oscillator, what we call a momentum oscillator, will be able to spot this type of behavior. And in conclusion, what I'd like to say is, in elastic applications, and when we talk about cloud deployments, we're talking about elastic environments. And elastic environments, really, you can't apply static models or static behavior models or topology models because they simply would not work. Topologies change, behavior changes, loads change, basically anything about application might change. The fact that you also have, we talk about patches to the application could be delivered in an agile development process. Things can change as well in the application and the business logic. So you need a completely different approach. You can't use a static approach. You need to combine data collection with dynamic pattern detections, dynamic topology discovery, which is by actually analyzing transaction behavior, because you can't use it, you cannot just put up a Visio diagram and say, well, this is my application work, because tomorrow that Visio diagram will be most likely invalid. And you have also complexity of systems. You have complex systems layered on top of other complex systems, which makes really root cause very, very difficult. And hence, I was kind of trying to show some of these tools that you use in order to facilitate not just the early detection, but also root cause analysis. For example, for transaction, when you're tracing transaction, one thing you can detect that is a problem, but the other thing is, well, show me where there may be a potential, what is this? Is this a database problem? Is there a problem with the data itself? So having the ability to be able to trace through these layers, identify the root cause, becomes very critical. Otherwise, you're again going to be throwing hardware and software into the problem, spinning other VMs, and it's not really an efficient approach. And again, preferred approach is this holistic monitoring. Really look at each individual tier, each individual layer, like infrastructure as a service or platform as a service, application. Identify specific key performance indicators that you need to use for each one. Layer transaction monitoring capability. Now, you don't have to necessarily monitor every single transaction, but at least monitor important transactions that matter to the business. And then combine it with trend analysis and analytics. Now, some of the things that I've shown you, they were fairly simple. I like to use simple techniques that give you, a high yield. You obviously can use much more complex analytical tools, which take into account not just KPIs, but also take into account topology and configuration and interconnections. But you need to do a lot of work and you need to have a big base of existing tools and configuration management databases in order really to make sense of that. So in conclusion, it's really, trying to make it simple, use some, key analytical tools that help you figure out what's normal or abnormal, being able to track transactions across different tiers, and also being able to take actionable, some action as a result of those indicators that you monitor. I'd like to open the session for questions. If you have any questions, please let me know. There you go. Well, typically with static thresholds, you have it's a static threshold. It's basically somebody's guess as to what it should be, typically done by an interview process, right? You're talking to somebody who says, well, what should it be? And you set those up. Invariably, in elastic, again, environments, especially cloud environments, it's not really going to work because the threshold is always most likely wrong. It doesn't take into account all of the variables. So using dynamic thresholds that take into account, behavior will allow you to now eliminate, maybe not all, I wouldn't say they will eliminate all false positives, but will dramatically decrease it by probably 80, 90%. So I've seen environments where they're getting really thousands of alerts every day. They want to eliminate that and reduce it by 80, 90%. If you can reduce it by that margin, it's a big win already for many shops. Obviously, you won't be able to reduce it down to zero. There's always going to be a few that will get through, but it will reduce it by a big margin, again, using dynamic models of behavior. Any other questions?
Just wait, adding on to that, do you start with the same thing with two dynamic thresholds? What's normal over a 7 period or a 14 period?
Well, you use real-time and historical, right? So you kind of combine both. Now, you can use completely real-time, which means anything we would store in memory, let's say 15 to 20 minutes worth of data. But if you want to do long-term, like what's normal during this day, what was it normal during, last week, you obviously have to store it historically. So it's really both. It's not just one or the other. You really have, in my view, you have to really combine both approaches, because a lot of times you want to know what is that, is there abnormal behavior right now, right this right this past, 5 or 10 seconds or, 10 minutes. And then the other approach, another thing is you want to look at, well, is it normal for this day or is it normal for this week? That's a different question. It's a more longer term question, but in my view, you have to really combine both. Yes?
What's the recommended offline storage?
It depends on the amount of data you want to collect. In many cases, SQL is okay. I mean, it could be a big SQL storage, but in many cases, what we find is it's inadequate when you're talking about terabytes and terabytes and terabytes of data, especially for shops that want to maintain. They want to store everything, analyze everything. Typically, you want, in that case, go to some kind of a NoSQL type storage. It could be Cassandra, Hadoop. There are many others, non-standard technologies. But keep in mind, in that case, they are non-standard, as I mentioned. There's not one interface that you can just write to, right? Each one has its own paradigm, its own implementation, its own deployment. So it has its own set of challenges that you need to deal with. But the benefit of that is you can plug in as much of that, on-demand storage. It's kind of cloud-based storage. You can make it, as much as you want. But the downside is you need to be able to manage that properly internally. If you need just a few weeks or a few months of data, it's probably okay to use SQL up to a certain point. The other thing is you need to also look at the recovery times. What happens if the database goes down, and how long will it take for you to recover? As the database grows, these recovery times start growing as well. And it depends, again, on the business. Some of them say, well, an hour recovery is not adequate for us, and therefore they need to go a different route. In other cases, it's completely, it's okay, and then SQL is acceptable. So SQL for, I guess, less demanding, and then I would say NoSQL for, high volume storage and, real-time analytics. That's what I would say. Thank you.